Welcome everyone to another OCP Tap session. This is call number 110. And today we have Professor Jason Eshraghian. Jason is a assistant professor with the Department of Electrical and Computer Engineering at UC Santa Cruz. He received his Bachelor of Engineering in EE and Bachelor of Law degree from the University of Western Australia in 2016, where he also received his Ph.D. degree in 2019. From 2019 to 2022, he was a Fulbright Research Fellow at the University of Michigan. He received 5 IEEE Best Paper and live demonstration awards, and serves as a scientific advisory board member for the Brainchip, also the secretary of the Neural Systems and Application Technical Committee, and as an associate editor for APL Machine Learning. So today's talk is about basically their work on how they use recurrence to eliminate matrix multiplying for large language models, which, as you guys know, large language models take a big chunk of like the processing power that is needed for LLMs. And why is this related, let's say, to this forum is perhaps because, again, we are a special interest group in timing, and perhaps like somehow these spike neural networks and all these topics, related topics that they come up, might be actually influenced or can be good applications for precision time, basically, in distributed systems. So with no further ado, Jason, the floor is yours.
All right, awesome. Thanks a lot. This is one of those talks where I've accidentally crammed in way too much information, so I'm just going to get started. This is going to be a very software-centric view of approaches to enhance LLMs and to reduce the power consumption of them. And as you mentioned, I think that there is a lot of relevance to timing, both from the spike side and in the, I guess, recurrence of language models. So we might know that language models are not by default recurrent. The ones that we are most familiar with in ChatGPT, Gemini, etc., they're using self-attention as the backbone, which doesn't really incorporate any sort of sequence-based modeling. That there are other ways to inject memory over sequences, but it's not really something that is processed step by step. So we'll start off with the kind of like a trajectory of where my lab's gone. We started working with spiking neural networks, this kind of approach to using ideas from computational neuroscience and in the sense that biological neurons communicate via spikes, and combining that with deep learning. So why the hell would we want to do that, right? So I like to distill this down to what I call the 3 S's. Spikes, this idea that biological neurons interact via single bit spikes, this cartoon depiction of a biological neuron. If I take this electrode and I probe this neuron body, then this scope's going to show me a lot of varying voltages. So it's going to be much noisier than what I've displayed on the screen. Now, if I take that electrode something like 1 or 2 millimeters away from the neuron body, then all of that voltage perturbation, all of that fluctuation is completely attenuated. And I'm only ever going to pick up signals whenever there is what's called an action potential or a spike or an event. So if that neuron body is sufficiently excited, it transmits this something like 100 millivolt voltage perturbation down to other downstream connected neurons. Otherwise, this axon, this wire, this cable is dead silent. And as digital designers, we like this because the occurrence of a spike can be presented as a 1. It's something that either happens or doesn't happen. There might be some variations between pulse amplitude, pulse width, etc., but we're not really sure if that's meaningful in the context of the brain. So, if there is a spike, we represent that as a 1. If there is no spike, we represent that as a 0. The x-axis denotes time. So if I was to take every artificial neuron in a neural network and replace it with one of these neurons, then you have a lot of zeros, you have a lot of sparsity. If I take 0, multiply it by a weight, then I just have 0, right? And that's a memory access that doesn't need to take place. If on the other hand, if I do have a spike, then 1 times my weight, that's just a memory readout. You kind of get rid of the multiplication, and all you need is accumulation. So we get something cheaper. Your second benefit it still arises from sparsity. It's this idea that biological neurons are actually very quiet. They spend most of their time at rest. Most of their activations are going to be 0 at any given time. I've got this silly little example of this list where I could read it out by saying 0, 0, 0, blah, 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 7, 0, 0, blah, 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 5. It is far more efficient for me to just state where the non-zero elements are, though, right? 7 at position 10, 5 at position 20. So you only increase the amount of memory that you're using for every non-zero element that you have. So if you need to start caching activations, this is probably a better representation. Something like run length encoding is what you want to do. And that way you can reduce the amount of memory that you're using. So if you have less memory accesses from this first benefit, you have less actual memory usage or cache usage from the second benefit. And thirdly, I'm not really going to go into this, but it's this idea of static suppression. It's the notion that our sensors, our biological sensors, so our retina, our skin, etc., they're only processing information when there is new information to process. So if I have an image in front of me, then that image is, I look at it, I've processed it, good. I don't need to keep processing every feature to it. This example that I've gotten drawn up here with the car in motion, for example, it's that the neurons that are processing dynamically changing data are the only neurons that are going to be likely to transmit data to your brain for further processing. So you have a sparse event-driven tensor, high-dimensional matrix that can then leverage the benefits of spikes and sparsity. So how do we actually take advantage of that idea of a spiking neuron in deep learning? Very quickly, I'm going to give you a very arm's length view because I kind of want to jump over to the linear recurrent models instead. But if we have this other cartoon depiction of a spiking neuron, you have a series of inputs, and if that neuron is sufficiently excited, both in space and in time, then it triggers its own output spike. It could be a 1 or a 0. More recently, people are relaxing the constraint of a binary activation and letting that 1 be some graded spike. So all we care about, if all we care about is sparsity, then it's not that your neuron has to be a 1 or a 0. It could be something else. And, computation is cheap. It's just memory accesses that are expensive. And so I kind of think that's okay. You can relax the assumption of binary spiking. And the rough idea is that, with the most coarse-grained model of one of the most coarse-grained models of spiking neurons is this leaky integrate and fire neuron, where you've got this thin film membrane this bilipid membrane. It's surrounded by some sort of ion, a saline solution with ions floating around, and the inside of that membrane also has some saline solution with ions floating around. And if you consider that membrane to be an insulator, then you've basically got a conductor, insulator, conductor. We know that to just be capacitive, right? And we also know that ions are moving in and out to achieve some sort of equilibrium, whatever that might mean here. That can be modeled as a resistor. Of course, it is a highly dynamical system, not just a linear resistive ohmic situation. But if you have an RC circuit, then that can be very easily modeled by a low-pass filter, right? With this current injection that resembles the various input spikes that are coming into this neuron. So the idea is that the neuroscientists stole from us EE folk in order to model their neurons. So it's time to steal back from them and use their neuron models in order to hopefully make our neural networks cheaper. And so qualitatively, I don't want to lose people behind the math of it all, but qualitatively, if I have some input spike, then the membrane potential will jump up, exponentially relax back to some steady state value, normalize to 0. And if you get a spike train, then you're going to start seeing the membrane potential accumulating. So we've got integrate in the form of accumulation. We've got leakage in the form of exponential relaxation back to a steady state value. And if that membrane potential voltage, the voltage across the spike, across the capacitor, reaches some threshold, then it triggers a spike. And so the thought is that if in a world where you're using binary spikes, how do you represent information then? Typical deep learning represents it in, I guess, the amplitude of the neurons in your model. With spiking neural networks, it could be the firing rate, it could be the spike time. And so that's kind of what we're considering, where we're trying to figure out alternative strategies to train spiking neural networks to consider when to spike at the correct time or with some given rate. So this can actually be I guess, recast as a recurrent or a recursive equation, where down below here, I've got this membrane potential update equation. Beta is between 0 and 1. So you've kind of constantly got this decay factor, this decay back to steady state. And the spiking dynamic is just a heaviside function with a threshold shift. So if your membrane potential is greater than the threshold, you get a 1. Below the threshold, you get a 0. This can be represented as a recurrent neuron. And we know how to train recurrent neurons thanks to people from the 1980s in the deep learning community. I guess it wasn't very deep in the 80s, but you just unroll your computational graph over time. So rather than taking XW as your input current injection and just looping it back around, every time you loop, instead you explicitly unroll your graph. So you've got time moving forward from left to right. Your input current is represented by the multiplication between X and W. X is your input, W is a learnable parameter. V is your membrane potential, which is decayed by a factor of beta at every single time step. And then you threshold your membrane potential in order to generate a spike that is either going to be 0 or 1 at every given time step. So the idea is that if you have this acyclic computational graph, then you can use all of the tricks and all of the hacks that go with training deep learning models to optimize these things, which is honestly kind of vanilla. It's pretty straightforward. And except for the subtlety that your membrane potential and spiking dynamics are related to each other via this heaviside operator. If your membrane potential is greater than the threshold, you get a spike. If it's below the threshold, you don't get a spike. And the thing is, optimizing this, trying to find the best value of W, and keep in mind, this is just one neuron simulated or expressed over 4 sequence steps. In reality, you might have millions or billions of neurons with millions or billions or even trillions of weights now. And so you're using the chain rule iteratively to update your weights. And so you're taking all of these partial derivatives. And if I take the derivative of S with respect to V, then I get this Dirac delta. And you're taking that, I guess, Dirac delta function, which is 0 almost everywhere, multiplying it by every other gradient. And then suddenly your weight update is 0 or infinity, right? So there's no real learning going on there. Now, thanks to quantization-aware training, and we know that the training process is quite tolerant to gradient approximations. That's all we do. During the backward pass, we use a gradient approximation, which is super simple. There's been a lot of hyperparameter searches to figure out what the optimal way to train these things are. In the quantization-aware training literature, people just ignore this step during the backward pass. They use what's called a straight-through estimator. That is, you just pass straight through the non-differentiable operation and skip that. It's just like setting ds on dv to 1. In our case, we find that, using something that better resembles this heaviside operator, just smoothed out a little bit on the backward pass only, that helps a lot. So your forward pass still achieves sparsity by doing a thresholding function. Your backward pass is smoothed out. That's all well and good. Pretty basic ideas, if I may say so. But you can optimize, you can train reasonably large models using this approach. There is a limit though, but before we get there, we've kind of rolled all of this up, and I developed SNN-Torch back in, I want to say 2020, the onset of COVID, which just makes this whole process far easier. It's an open source Python library that it's a thin abstraction layer on top of PyTorch. So the developers of PyTorch really did all the heavy lifting for this to be possible. It enables a few extra features like real-time online learning. It works together with PyTorch. So if you're familiar with PyTorch syntax, you have nn.linear to generate your current input, and then you have SNN neurons, SNN-Torch neurons to actually do the recurrent operations with thresholding, with gradient overrides. It's accelerated for CUDA and some other accelerators, but it's also become compatible with neuromorphic hardware that's being developed by Intel, some startups as well, SynSense, etc. A few cool places have taken advantage of it as well. And if you want to go deeper into it, I've written up a very rigorous set of tutorials that kind of help you from the ground up. So there's Colab notebooks, so there's interactive code, etc. Won't go into that, but know that this exists, and it's pretty easy to find just by searching up SNN-Torch. Let's get a little bit more formal about it. And I want to get formal about it because I really need to show you how if these can scale up to more complex tasks. Because if you look up spiking neurons or spiking neural networks in Google Scholar, you're going to see a ton of very much toy simple problems, things that the deep learning community do not take seriously. We see a lot of MNIST, CIFAR 10, ImageNet, things that are kind of considered solved amongst the deep learning practitioners. So let's get a little bit formal about it. Let's consider what one layer of spiking neurons might look like. Let's say we have 3 inputs, x1 to x3. Each of those gets passed into this recurrent neuron, which we know is spiking because we're doing some threshold function. I'm going to say that, x1 is going to be scaled by, now I've replaced beta with just W superscript. So W1, W2, W3 are between 0 and 1. That's our decay factor to ensure exponential relaxation of the membrane potential. If I want to have some simulation at t equals 1, then I'm going to get some hidden states, the membrane potential, denoted by V. That's going to be W1, W2, and W3 scaled by this vector of my previous hidden states, V1, V2, V3, denoted by this subscript of 0, with the extra current injection input. So if we kind of sequence this step by step, we just get W1 times V1, and 0 times V2, 0 times V3. So really, the hidden state of this first neuron is only a function of V1, but I've denoted this as a matrix because the recurrent neural network literature has a dense square transition matrix. Your second row, V2, is just a function of W2. Your third row, V3, is just a function of W3 times V3, and X3, of course, as well. So that can be simplified. You can kind of collapse this diagonal transition matrix into a vector that just does a Hadamard product. So W1 times V1, W2 times V2, W3 times V3 to respectively give me V1, V2, V3, plus my input current injection. And I can increment over time. So t equals 2 just updates everything by 1 time step, and you just keep doing this ad infinitum. All right. That's all well and good. That's how spiking neurons. You just do this across a bunch of layers. You use your gradient overrides, whatever. You manage to optimize something that can do pretty simple tasks. Let's consider the subtle difference with recurrent neural networks. So just like before, we have x1, x2, x3 being fed into 3 neurons. The difference here is that we now have the hidden states of these 3 neurons, the V1, V2, V3 values, that are now being projected into their own linear layer, like their own dense layer, which can be represented using vector matrix multiplication, followed by some nonlinearity. TANH, ReLU seems to be the defaults of choice in PyTorch. And then they're just added back to x1, x2, and x3 to update the hidden states. So formally, this looks like this. Your hidden state is now a dense transition matrix multiplied by the previous times hidden state with the input fed into that. And so we can see that W1, W2, W3 are scaled by V1, V2, V3 to give V1, which kind of resembles this mixing of hidden states. So in a way, the membrane potential from spiking neurons is now going to influence the membrane potential of every other spiking neuron in this picture, which biologically doesn't make sense because membrane potential is like an isolated feature. It's only spikes that are being communicated, but recurrent neural networks don't care about biological plausibility. They just are the way they are. So in addition, you also have this nonlinearity applied before you add your transition matrix multiplied by V1 to V3 to your input. So RNNs versus SNNs, we can kind of see a few face value differences. They are that with RNNs, you have what I like to call all-to-all recurrence because every neuron is influencing every other neuron, right? And you also have nonlinearity over time. So the next hidden state is a function of a nonlinearity. On the other hand, with spiking neurons, there's only one-to-one recurrence, right? My hidden state of neuron 1 is going to only affect the hidden state of neuron 1. And it's linear over time. Now, there is also this kind of thing that spiking neuron folk like to add this reset mechanism. So every time you get a spike, every time there is a spike, you subtract that spike from the hidden state. That is just to inject sparsity. It's this phenomenon known as hyperpolarization in spiking neurons. So you get nonlinearity if you introduce that reset mechanism because S1, S2, S3 are a function of a Heaviside operator. This is important for a reason that will be obvious in a moment. But those are the high-level differences between SNNs and RNNs. As a bit of a preface as well, before I get into some details, you'll notice that spiking neurons have, for 3 spiking neurons, I have 3 learnable parameters, W1 to W3. For a conventional recurrent neural network, I have 9 learnable parameters from W1 through to W3 by 3, W9, right? So we would expect that spiking neurons probably suck compared to recurrent neural nets for 2 obvious reasons. One, we have far fewer learnable parameters. and two, the way we use nonlinearity. So one, we have a nonlinearity over time, which may help with the universal function approximation theorem. And two, we're binarizing our output activations to 1 and 0. So that latter point is going to degrade the performance of spiking neural networks, which is why people have gone towards fixed precision activations with a lot of sparsity. So it's just think of like a shifted ReLU, for example. But otherwise, this issue with having more learnable parameters in RNNs versus SNNs, that's something that we'll get to. Before we get there, I want to highlight some of the pain points of SNNs. So software pain points and the hardware pain points. So software pain points, nonlinearity through time due to reset. I'll raise why this is a pain point in a bit. And we also have weak representational capacity as a result of binarizing activations. The hardware pain points is something that the communication cost is really what data movement is really what dominates hardware costs, right? In terms of energy and latency. So we don't really need single bit computation. All we need is sparsity. And secondly, dynamical workloads are very prevalent in SNNs, right? You have a lot of asynchronous hardware that accelerates spiking neural nets in that many of your neurons may be quiet. So why send a clock to those particular neurons? Rather just let everything be data driven. And the issue with that is, I think it's kind of obvious, right? In the case of modern vanilla accelerators, you're transferring tensors from one processing element or from one block to another block. You know exactly what's being transmitted from one time step to another time step. Everything is quite deterministic. You know exactly how long one layer of processing is going to take. With spikes, if in some, I guess, pathological case, I had every single spiking neuron active versus a case where no neuron was active, some sort of asynchronous processor would have non-deterministic, I guess, latency, right? We don't know in advance of actually running some workload how long this process will take. And so that introduces its own set of challenges. And of course, the other challenge being that asynchronous design is pretty damn difficult. So there are various chips and accelerators for spiking neurons and variants of spiking neurons out there that just do fine-grained clock gating and things like that. So Brainchip, for example, go in that route. So why do we care about linear recurrence? Why do we care about linearity through time? So recall I made a bit of a point about the reset mechanism introducing nonlinearity through time. Now, the neural network community loves nonlinearities because that's why neural networks can represent or approximate any arbitrary function because of sigmoid, because of ReLU, etc. Now, I want to distinguish two things. I want to distinguish nonlinearities through space, where let's say you have two neurons connected to each other and you have a nonlinearity of your activation as you move up through your layers. And I want to distinguish that from nonlinearity through time, where you have one neuron that has a weight up, that has a hidden state update or a membrane potential update for spiking neurons, where you apply a nonlinearity over time. So that is a reset mechanism. That could be the tan-H function for RNNs. So those two things are very different and they have very different implications. Now, it turns out that linear recurrence, so linearity through time, is quite critical to being able to scale up RNNs and SNNs. Let me explain why. Let's say that we have this RNN with 3 inputs. Let's use an SNN instead. Let's say this is a spiking neuron with 3 inputs, and these 3 inputs are denoted as X, X1, X0, X2. Let's say each of those have their own various valued spike, spike of different amplitudes coming in. And what we get is a membrane potential that evolves like so. If I was to update my spiking neuron hidden state V sequentially, then we end up with time complexity that scales with the sequence length, right? With the sequence length being denoted as T in this particular case. The same is applied to backpropagation, right? In order to train one of these things, I need to apply backpropagation through time. I need to accumulate a set of gradients that are traversing backwards through that acyclic computational graph. So sequential computation makes training untenably slow. An alternative way to process these things is something that looks a bit more like a kernel, where epsilon might just be some exponential relaxation kernel. And then I can decouple the effect of all of these spikes. So one spike gives rise to this particular kernel. This other spike gives rise to this other kernel. And this other spike gives rise to this other kernel. Then I can just add these 3 separate membrane potentials together. And that scales with log n complexity. So that is far, far more efficient. Now, I would not be able to apply this exponential kernel approach. I would not be able to get this decay the moment I introduce nonlinearity. Why is that? So intuitively, recall the case with a spiking neuron, where if I get a threshold crossing, if my membrane potential crosses a threshold, I get a spike. Now, if I want to include a reset mechanism, then I subtract that spike from the membrane potential, from the hidden state. Now, from these three plots, until I've accumulated the membrane potential from these three plots, I don't know when a spike is going to occur, right? Now, I don't know when a spike is going to occur, and therefore I don't know when I need to do a subtraction. And then I would need to reprocess everything from that nonlinearity onwards. And so nonlinearity over time breaks parallelism. It precludes me from being able to train models with log n complexity, right? So keeping that kind of stored in the back of our minds, I want to move on to spiking language models and what we've done with SNNs in the language domain, because like I said, a lot of SNNs have only been really targeting toy problems. So we trained Spike GPT. We developed the largest spiking neural net that was trained using backprop and gradient descent with gradient approximations. And it was the first to perform language generation as well. We did 3 variants of it, the largest being 260 million parameters. We did go up to 1 billion parameters with some caveats there. Briefly, some performance samples. Look, if I showed you this 2.5 years ago, this would be very impressive. Now, I don't think we really care given how far ChatGPT has come. But the way that we effectively achieved this was treating this model as a linear spiking neural network. So we didn't include reset mechanisms. We were able to train this whole thing in parallel with log n complexity. So all of your inputs across X are passed in parallel. You can calculate, you can obtain various kernels all simultaneously, take advantage of all your cores without having to wait for one particular sequence step. You don't need t equals 1 in order to process t equals 2. And additionally, but during inference, it is processed sequentially. We also added in one extra factor. The weights change over time. The weights are data dependent. And so that is something that's kind of taken off in recurrent language models recently. And I'm going to go into more detail on this when we get to the MatMul-Free model. All of the modern language models at the time of publishing this were not dynamic. The models would be trained, fixed, and that's it. They required all of your input data to be available in parallel, right? When you're typing into ChatGPT, you pass your data into the model once you've set up all of your input. So Spike GPT and recurrent language models just kind of take data in one at a time. You can start processing on data before all of your data is made available. So as a result of that, we were able to get a few benefits. We were getting 30x less operations than a transformer of equal size, thanks to dynamic weights, thanks to sparsity in our activations, and all of that. So my question is, why isn't the world using spiking neural networks for language modeling? Scaling hurts. We tried to train a model that went up to 1 billion parameters. And so for context, for those of you that might not be familiar, we expect GPT-4 to have something like several trillions of parameters compared to our measly 260 million or 1 billion. This is, 3 orders of magnitude smaller. And scaling hurts, right? We try to train a 1 billion parameter version of this Spike GPT model, and the performance improvement was very, very small over the 260 million parameter case, which was kind of a shame. In a way, it kind of deflated us. It made us think, what we're doing right? Is what we're doing in spiking neurons the way forward? I think that part of what we're doing is correct, part of what we're doing is not correct, but I'll kind of wrap up some of these lessons that we've learned into a nicely packaged summary slide at the end, so I can kind of give you an honest opinion of where we're going with this. But to move forward, we basically relaxed a bunch of the issues that I found with spiking neurons. We kept it recurrent. I still feel like things that change over time make a lot of sense. And for me to kind of drive home why recurrence is, so historically, recurrence is all we had in the deep learning world in order to process sequences of data. We then moved over to self-attention because there was a bit of a challenge with memory in recurrence. And what I mean by that is this. Let's take this intentionally ambiguous sentence, Sundar saw Mark with binoculars. Now, my question to you is, who has the binoculars? Is it Sundar, is it Mark, right? Linguistically speaking, either of them could have the binoculars, right? Sundar could be looking at Mark, and Mark is holding the binoculars. Alternatively, as humans, we have enough context to know if Sundar is looking at someone, he's probably looking at them with the binoculars, right? So there is no correct answer. All we have is a sufficient probability based on our experience that Sundar has the binoculars. Now, self-attention looks at a very high level. Self-attention is the backbone of all modern language models. It looks something like this. It takes every token, it takes every word in your sequence, it breaks them up into smaller constituent parts, and it finds their attention score with respect to every other word in this sequence. So what I mean by this is you have a matrix with a bunch of numbers. Sundar and binoculars, the correlation between those two words, those two tokens might be quite high. There might be some strong correlation between Mark and binoculars, but it's not as strong as that between Sundar and binoculars. Therefore, we expect Sundar to have the binoculars. So self-attention has access to the entire input sequence at any given time. And so it has really good memory. It can learn things pretty effectively, and that's why it's used so widely. If I was to replace this with a recurrent model, then I'm going to feed in every word step by step, one at a time. I'm going to get exponential decay. I'm going to lose information as we go forward. So by the time that we get to binoculars, the relation between Sundar and binoculars may very well have faded and been replaced by additional input context provided by Mark. And so this is a very simplistic toy example just to give you intuition. It may not be what's exactly going on under the hood, but I feel like it gives the right feeling of the right spirit behind self-attention versus recurrence. Attention, in a way, has too much information. There's a lot of redundancy. You've got this huge matrix full of information that you don't need, but it's effective. On the other hand, RNNs are cheap, right? They're effective, they're cheaper than attention, but there's not enough information there. So my goal here is to bridge these two things. Spike GPT suffered from the lack of information. It did well, but it didn't scale very effectively. It did far better than any other SNN at the time, but there was still a bunch of shortcomings. So in order to kind of address this, I'm thinking, what are the pieces of self-attention? What are the constituent components of transformers that enable such good performance, right? Well, we have token mixing. Tokens refer to the various constituent components of your input sentence. And you're mixing tokens. The act of mixing tokens implies that you're mixing information over time. So the generation of an attention matrix implies that we're doing some sort of mixing over time. We're mixing binoculars with Sundar. We're getting token relationships between the first token and your final token. So you're mixing information over time. You also have this second thing called channel mixing. So these tokens are represented by numbers. These numbers could give a sense of the meaning of words, of individual tokens to your model. And so you're mixing vectors that represent tokens, that represent words via channel mixing through feed-forward layers and things like that. Then we also have residual connections. We also have layer normalization. So residual connections is just the act of projecting information from one layer to several layers ahead, to 2 layers ahead. So they're skip connections, right? Layer normalization is just doing some sort of normalization operation across activations. And these latter two are strictly for the purpose of improving gradient flow during backpropagation, which has enabled training such deep models. So it's really these first two things that I'm really interested in, especially token mixing. Now, in a way, RNNs are also a form of token mixer, right? Where we're in this unrolled acyclic computational graph, Sundar goes in and gets decayed over time. It's getting mixed. It's just not a very efficient mixer of information, but it is a mixer. And that's the point that I want to drive home. So my question is, what are the alternatives to self-attention, and how can we kind of bridge the gap in performance with self-attention? Now, this is more of a tutorial rather than what work we've done, but the alternatives to self-attention that have emerged over the past 12 months since Spike GPT can be boiled down to full-length, one-dimensional convolutions and RNNs. So those are the two dominant alternatives to self-attention. Let me give you a sense of what they do. For full-length 1D convolutions, they look something like this. Let's say that we have a one-dimensional convolutional kernel, right? And it's a 2D matrix, but it's one-dimensional in the sense that the kernel is only moving across one dimension. And that is my blue matrix. So these are the learnable parameters. Then my matrix in green, every column of this green matrix represents another token. So it could be that this first column represents the word Sundar, the second column is saw, the third column is Mark with binoculars, and so on. So from right to left, we have additional tokens representing different numbers. And so This full-length 1D convolution, it's full length because the dimensions of your convolutional kernel match the dimensions of your input sequence length. And the way this goes is something like this. So we take the 3 elements of my first token and the 3 elements of my convolutional kernel, keeping in mind that it's not really 3 in practice, it's more like 512, 1K, 2K, 4K, etc. And we just do this Hadamard product, element-wise operation to generate the output of this layer. Then we scan the kernel across one column. We repeat, and we repeat again. And we repeat again. We've now generated 4 target embeddings, and we're just going to keep doing this with the kernel sliding out of sight, right? But what's kind of interesting in this picture here is the benefits now. The first token and the final token are now interacting in this target 4 embedding, right? So your first token has access to your final token. Self-attention does that as well. You generate an attention matrix where every token has access to every other token. Now, in this target 4 embedding, it's the same picture. And so that enables long-range memory, right? Your neural network, your language model is able to store contextual information from something that occurred way later to something that occurred way earlier. So you've got that long-range context. The cons, they only interact for one time step, right? So it could very well be that this target 4 embedding is the only output activation vector that contains information from the start and the end. Target 1, 2, and 3 did not contain information from both the start and the end of my input sequence. And so it is very likely that this target 4 embedding kind of gets swamped out. And as a result of that, it does actually have, it still underperforms compared to self-attention as a result of this. Another issue is that the hidden state has to expand for longer sequence lengths. So it's kind of like saying the number of target embeddings in your convolutional kernel are still scaling along with an increasing context window. So if I increase the length of my sentences, if I want a neural network that can operate with very long PDF files, I mean, Gemini and whatnot are seeing 100K, 1 million tokens of context, then I need a 1 million by 1 million convolutional kernel, and that is painful. And additionally, inference complexity is still greater than that of recurrent linear neural networks. And so for those reasons, people kind of started working on full-length 1D convolutions, say 12 to 24 months ago. I wouldn't say that they've been completely abandoned, but people have largely migrated over to linear recurrent neural networks as a result of these drawbacks. So for that reason, we're just looking at recurrent neural networks as an alternative to self-attention. But of course, there are a variety of reasons why people moved away from RNNs and over to self-attention. So what are those challenges? So one, training RNNs requires backpropagation through time. A longer sequence length means a longer acyclic computational graph that needs to have gradients calculated and propagated backwards through. The second challenge, you're still relying on vector matrix multiplication through time. And I'll quantify this in a bit more detail in a moment. And perhaps most importantly, it has poor long-range performance. Now, if 1D convolutions had bad memory with increasing context windows, RNNs are historically far, far worse, right? So with that being said, let's try to address these one at a time. How do we address backprop through time? Let me give you a sense of what backprop through time even is. Let's say we're bringing back that spiking neuron model. If I want to optimize W, then imagine I have some loss function that penalizes my neural network. I'm going to go backwards and apply the chain rule iteratively through every single forward pathway in order to get DL over DW, but I have to do this again and again for every single time step. I'm calculating many, many partial derivatives. This doesn't even account for all the temporal pathways where we go backwards through time again and again. So these arrows are now hopping backward one step. We need to hop backwards 2 steps as well now. We need to do that, and then we need to hop back 3 steps. So it just gets more and more complex as you introduce more time steps and more layers. So time complexity of backprop through time scales linearly with your sequence length T and with the number of neurons N. We want to avoid that. And this is what I was getting at with respect to parallel training. Now, if you remove nonlinearities through time, then you can crush that linear time complexity down to log n time complexity. You can also remove the learnable parameters in time, but I'm not going to go through that. There is one concern, though. Is the removal of nonlinearities over time going to break the universal function approximation theorem? And there was a paper from, I want to say 3 or 4 years ago, that conjectured that as long as you have nonlinearities through feed-forward layers that are then interposed with some token mixing layer, such as a linear recurrent token mixer, then you're able to preserve nonlinearity. So you're mixing information that already has a nonlinearity applied to it. It's just that your hidden state doesn't require a nonlinearity itself. It's just kind of like your X value, your current injection into your RNN that has a nonlinearity. And so there are generally two types of linear recurrence that I've observed in the literature in the past 12 months. One is what you see here, exponential moving average. I'll call that a static decay. This is where beta is between 0 and 1, and you get exponential decay to a steady state value. But there is also the addition of gating mechanisms. And so that is called data-dependent decay, where your decay, beta, is now a function of your input data. And so then you can get far weirder dynamics. And it turns out that introducing data-dependent decay really helps with bringing back some of that memory. And as long as you do it in a linear fashion, that is to say, I don't apply a nonlinearity to beta VT or to XT, then I'm able to train this with log n complexity. So the challenge of backprop through time is kind of addressed there. And just to give it a little bit more intuition on why this is so important, imagine that, let's say that an RNN with a nonlinearity over time has better learning capacity than a linear RNN without a nonlinearity over time. Then, okay, sure. Theoretically, that nonlinear RNN may be able to learn something just a little bit more than that linear RNN. But that in the time that it takes to train that linear RNN, or at least in the time that it takes to train the nonlinear RNN, I'm able to train 100x more tokens on my linear RNN, and that would completely offset the performance given a certain amount of compute. So given a set of operations, sure, my nonlinear RNN may be able to learn more than my linear RNN, but given a particular amount of compute, which is a far more practical engineering-centric problem, my linear RNN will always be able to train much faster on far more tokens, and that's always going to outperform given the same computational budget. So I now want to go over to vector matrix multiplication. And I should mention that this is kind of where we're going into all the techniques that went into the matrix multiply free model. I'm seeing a few things in the Slack. Yep, so sorry, in the group chat. Yep, so feel free to keep any questions coming and I can address them towards the end. Reliance on vector matrix multiplication. So why is that an issue? How can we get around that? Let's bring back the vanilla RNN update, the hidden state update equation. So we've already seen this. I'm going to vectorize this operation into this vectorized notation where V1 just equals my transition matrix multiplied by the hidden state from the previous step plus some input. Now let's say I want to calculate the next step of my hidden states, denoted by V2, the subscript 2. Let's substitute V1 from the top line into V1 in the bottom line. So I can expand this out and I get this form. And if I was to expand what's in this bracket, then I would get W squared times V0 plus some other stuff. So the point here is that as I increase the number of steps, the index that W is raised to just keeps going up, right? So to get V3, I'm going to need to take a cube of W and so on and so forth. So that's matrix multiplication. Then it becomes matrix multiplication and so on and so on. That scales cubically with complexity. With the linear RNN case where the transition matrix was just a vector rather than a dense matrix, we go through the exact same set of operations. We get W squared. The math there is exactly the same, just with this circle dot denoting an element-wise product, Hadamard product. Now all we're doing is just scaling, where we're just squaring every element of that vector, right? So we're not doing matrix multiplication. It's just a vector times a vector, which is just an element-wise product. So that scales linearly with the number of neurons n, right? The concern about that is am I sacrificing too much to do this? If I'm compressing a dense matrix of 9 learnable parameters or n squared learnable parameters down to n, I'm certainly losing something, right? And it turns out that you're not actually losing that much. Now, this is hopefully going to be the last bit of math-heavy slides that I show you, but it should be easy to, the intuition is easy to follow. So just accept that, you can diagonalize any square matrix. So you could use eigenvalue decomposition, singular value decomposition, whatever decomposition. We end up with PDP inverse. P could be eigenvectors, D could be the eigenvalue. So D is denoted as D because it's a diagonal matrix. And then we take the inverse of our eigenvalue matrix. So let's say that our transition matrix W can be diagonalized in some way, shape, or form. Let's bring back the hidden state equations that I've already shown you. So the hidden state equation from V2 is a function of W2. It is W raised to the power of 2. What does that mean? It's just like taking W and multiplying it by itself. PDP inverse times PDP inverse. And you can probably see where this is going, right? You can see P inverse times P cancels out to the identity. We end up with D times D, so D squared. That is a diagonal matrix squared, right? Diagonal matrices can be collapsed back into their vector form into like an element-wise product. W to the power of 3 is just going to be that same diagonal matrix to the power of 3, where P and P inverse are just untouched over time. What does that mean? We're able to represent this hidden state update in a way that has computational complexity that scales linearly. That's pretty good. And so the idea is that we're not losing any representational capacity in doing this, right? The problem with this is that calculating the inverse of a big matrix that could be 1,000,000 times 1,000,000 is very expensive. And so what the deep learning community has done is that this is where they detach themselves from theory and they just say, all right, let's just replace P inverse with another learnable matrix Q. So it's like saying that P is a channel mixer. It's just a dense layer, a feed-forward dense linear layer with a nonlinearity. Q is another learnable matrix that comes after the recurrent layer, and D is our linear token mixer, right? And so this kind of fits in with all the theory that where I mentioned that having nonlinearities over space and linearity through time is totally acceptable. So we're applying a nonlinearity to P, nonlinearity to Q, and our recurrence just needs to scale linearly, and that gives you an equal representational capacity to an RNN, right? So that's quite nice. I should mention that this substitution does mean that PD squared Q is no longer a perfect equivalence to W squared. But the point is, it doesn't matter. As long as you have equal representational capacity, that's what's key. And so I want to take a moment to kind of show you what's going on in the literature at the moment. So if you do eigenvalue decomposition, you could have real eigenvalues. So D could be a diagonal matrix of real numbers, in which case, if those real numbers are between 0 and 1, then you'll get static decay. It is also possible for these values to be complex, in which case your hidden state can also become oscillatory. And so you get oscillatory decay. Just look at RLC circuits, I guess. And in that case, this is kind of nice. And the intuition behind why this is nice, where we're kind of ticking two things off our checklist. One is linearity over time, right? We're able to get D squared. So D squared, D times D times D is just a linear operation. We're getting additional memory. So not hardware caching memory. I'm talking about memory in the software construct where your first token and final token have a memory of one another. Your final token remembers the first token. In the sense that let's project Sundar saw Mark with the binoculars over time T. By the time that we get to binoculars, your hidden state that relates to the first token might actually bump up. So it's not like information is fading over time. You get a bit of oscillation, and it's possible to get a perfect oscillation without any decay as well. So as a result of that, complex eigenvalues do have some value here. So we've managed to eliminate vector matrix multiplication. We're just doing element-wise operations over time in the linearity, in the recurrent pathway. The final and most significant issue was partially addressed. The poor long-range memory performance was partially addressed in the second issue with complex eigenvalues, but let's see what else we can do to really improve performance here. So the literature has gone over 3 different techniques for the most part to address poor long-range performance in RNNs. So one of them is the introduction of gating mechanisms, and this can be dated back to 96, where LSTMs came about and they introduced control and forget gates. The second approach was your diagonal matrix, your transition matrix, was regularized and normalized and initialized to something close to 1 to avoid sudden decay or sudden explosions. So it's something that kind of retained memory over time. And the final approach used temporal residual connections, where if we have an unrolled computational graph over time, it's just like projecting and pushing information to future sequence steps. The MatMul-Free model does these first 2 things. So everything I've described so far is integrated into the matrix multiply free model, but we also added in some interesting gating mechanisms that I want to talk about as well. Now, I don't expect people to recall what a forget gate is, so let me give you some brief intuition here, but let's represent numbers as colors for a moment, and let's say that we have 1 neuron unrolled over 3 sequence steps. We'll take a blue bit, whatever number blue that represents blue, and we'll pass that to our neuron. We'll move forward, we'll simulate 1 extra time step, and so the hidden state is now occupied by some blue bit. At the next time step, let's say that we want to introduce some additional information represented by this yellow bit. Now, unless I increase the memory capacity of this neuron, these 2 colors are going to mix. I've lost representation of blue and yellow individually, and so it's going to be this clunky green-brown color that gets pushed forward in time. Now, if I was to introduce forget gates, what might that do? So the idea is that having a forget gate lets you, in a somewhat controlled fashion, forget your hidden state. So if your forget gate is 0, then it's just like taking whatever that's in that inside of that neuron, multiplying it by 0, getting rid of it. If your forget gate is 1, it says, cool, I want to remember this. 1 times whatever your hidden state is retained over time. So if I do this again, if I take my blue bit of information, pass it through, I scale that by this forget gate 0, that opens up space for my yellow bit of information to move forward, untarnished by the previous blue bit of information. So in a sense, if your RNN has a limited amount of memory, then you need to be able to selectively forget information that you don't need. And that's kind of the trick to being able to make RNNs work effectively with language models, right? Of increasing context length. So what did we do? We took this idea of forget gates and took it a step further. Now, language models are composed of many blocks. Once upon a time, we were talking about layers. Now, individual blocks kind of have multiple layers within them, like 3 parallel linear layers with a bunch of other operations, and then we just repeat those blocks 24, 32, 48 times, etc. In billion parameter models, those would be about the number of blocks is about 24 to 32. So we set a lower bound on the forget gate of each block independently. And the motivation is something like this. If you think about the brain, now early regions in the brain, so early layers in the brain that are directly connected to your sensory periphery, they're just trying to find local connections. So in your vision system, layer 1 is trying to find edges. It's just trying to find contrast points of edges. Higher brain regions are starting to accumulate those edges. They're trying to get shapes. They're trying to get faces. The comp neuro community have this, sort of the theoretical neuroscience community have this joke about the Jennifer Aniston neuron, because you're trying to learn concepts and ideas rather than specific low-level bits of information. So in a way, that kind of has this, if we distill this over time, it's like saying early layers should be forgetting information quickly so that they can capture local relationships. And really, later and deeper blocks should have longer memory, that is to say, forget gates closer to 1, so we don't forget as much, in order to get more contextual information. So the way that the actual implementation was just applying a cumulative sum to the forget gates over the blocks. So if you randomly initialize a matrix and then you just sum up to ensure that lower blocks have lower bounds and higher blocks have higher bounds, and that means that block 1 has a forget gate that is closer to 0, and block 3, well, your final block ends up being normalized to having a forget gate closer to 1, so that deeper blocks don't forget as much, earlier blocks quickly forget information so that they can leave space open to process new things. And you kind of leave the task of forgetting and remembering to deeper blocks. And so doing that, coupled with everything else that I've kind of described, were the main keys to being able to make this MatMul-Free linear RNN work. So we've gone from this picture where we have attention with too much information to RNNs having the correct information. So we've ticked these three boxes off. And really, there's not much left to say about the MatMul-Free model, because everything I've described is kind of already is what we did for the MatMul-Free model. This is just a high-level overview of self-attention versus the MatMul-Free operation. The exact operations don't matter too much because I have gone through them. But if I was to distill this down to three different things that we did to make this possible, the first one is that your linear layers, or your feed-forward layers that typically rely on a vector matrix multiplication, all the parameters have just been replaced with ternary weights. So a vector matrix multiplication where your matrix has ternary weights just becomes a signed accumulation. So you can get rid of multipliers from that process. The attention map, the self-attention matrix, was replaced with all of that linear recurrent BS that I just described, with forget gates, with linear recurrence, with decomposition of transition matrices. And then finally, we ultimately wanted to, what's going on here? We wanted to actually show that this works effectively, because ternary weights, Microsoft did it really well in their BitNet paper. But, you know, GPUs have the best case. They have addressable memory blocked, I guess memory addresses of 4 bits, and so you can't really take advantage of ternary addresses in them. So we wanted to do something that was actually optimized. So we did our own FPGA implementation. I won't talk about the FPGA implementation here unless you have questions, but ultimately it's this first 2 points that enabled matrix multiply-free language modeling, and the last point that made it useful. So with self-attention, if I was to distinguish MatMul-Free from self-attention, with self-attention, you have some input X, an input token X that is passed through 3 linear layers in parallel, and then you end up with 3 output activations, and you do a bunch of operations on them. And what's critical here is that of those 3 output activations, you need to store 2 of them in the form of the KV cache, because for the next token, for t equals 2, you need to concatenate these 2 vectors to your next hidden state. So it's just another form of doing matrix multiplication, right? You're just extending your sequence length, you're extending the amount of cache usage for a longer sequence length. With the matrix multiply-free approach, your hidden state does not get expanded. Your hidden state comes out of some of your input hidden layers with some element-wise ops taking place. That hidden state is used to just update the next hidden state. So nothing is expanding with sequence length. So everything I described before, so backprop through time, that is addressed by having a hidden state that isn't expanding over time, that has no nonlinearity over time, right? The reliance on vector matrix multiplication is addressed by doing ternary parameters in the vector matrix mults, in addition to breaking self-attention down to something that, again, that just relies on vector-based operations. That's addressed as well. Poor long-range performance, everything that I described related to forget gates, related to input-dependent decay, all of that is integrated into the element-wise operations here. So that's kind of addressed here as well. So that's all well and good. You might be wondering, can't we just ternarize pre-existing language models instead? The cold hard answer was no. We tried to just ternarize everything to remove MatMul from Transformer++, which is the best open source kind of baseline, and it's the backbone of Llama 2, 3, Mistral, and a few other state-of-the-art models with variations. And the training loss didn't really converge when we ternarized everything in Transformer++, which gives me the sense that this MatMul-Free case that does converge well is able to, it's kind of maybe distributing, and this is just a feeling, right? It's distributing the compressed information in the form of ternary weights over time, right? So by distributing information over time, maybe that's doing something a little bit more effectively. I'm not going to go over the optimizations we made for GPUs, but just know that we did write some custom Triton kernels in order to accelerate training for this MatMul-Free language model. And I should mention that the MatMul-Free process is inference only. So we are still doing matrix multiply during training. The idea being that, you train once, you have a golden standard model that everyone's accessing. So inference is really what's that has the most upfront cost. We're doing gradient approximations because the act of ternarizing ternary weights, that is kind of like a pair of heavy side operators to be able to distinguish -1, 0, and +1. And so that's a non-differentiable function. So we have to do all the things we learned from spiking neurons over to MatMul-Free with respect to gradient-based approximations. There's some comments that I'll quickly make about the scalability of the MatMul-Free model. And it goes something like this. This graphic is taken from a paper about scaling laws for neural language models done by OpenAI. The plot in the middle here, that just shows the test loss decreasing with an increasing data set size. So for a given model, if I train on more data, our test loss goes down. On the right, if I have a fixed amount of data, then as I increase my model size, then I also get some decrease of test loss. And really, I need to combine these things in order to get this left plot where test loss decreases with additional compute, where PF days represents petaflop days. So it's more about how test loss drops with increasing compute. And what they note in this paper is that for optimal performance, all of these three factors need to be scaled in tandem. So inspired by that, we went ahead and explored the scaling law and how it applies to our model. And I have to say all of this with the caveat that this scaling law is as much of a law as Moore's law in that it's a projection, right? It's just a guess. So whether or not this holds true relies on getting access to more GPUs, having more resources for us to keep pushing this forward. But we are quite hopeful. On the y-axis here, we see test loss. On the x-axis, we have compute in terms of flops. And these dashed lines represent training runs for our MatMul-Free model as compared against Transformer++. So the dashed lines are what we actually ran. These semi-transparent lines are the projections. And so these two dashed lines for the 370 million parameter models of MatMul-Free as against Transformer++, you can kind of see that the performance gap, so Transformer++ does a little bit better, but the performance gap shrinks as we increase the model size. So the largest model size is our 2.7 billion parameter case with red versus this kind of purple color. And that gap is far smaller. And so the performance gets closer and closer for a MatMul-Free language model versus what is it? BrainFloat 16 Transformer++ state-of-the-art implementation, which I think is quite fascinating, right? And not just that, but we're normalizing this to flops. And the reality is that our model isn't entirely relying on flops, right? A lot of our operations are ternary computations. So we're kind of comparing against a far more expensive case. So if I was to account for that, then I feel as though our model would start to overtake here. But you know, we want to keep reviewers happy. We don't want to overclaim things. So we went ahead with this approach. And if you kind of accept this scaling law, then our slope is a little steep, just a little steeper, and it indicates that we should be able to converge performance somewhere between 10 to the 22 to the 10 to the 23 flops, which isn't that much when you compare it against what OpenAI are doing. So that gives us a fair bit of hope. But really what we need are just a lot more resources. We need more students and GPUs to make this possible, to show that we can keep scaling these types of models. This just quantifies everything that I described in a numerical way. So the gap between Transformer++ and MatMul-Free decreases as we get a larger model size across a variety of benchmarks. We also went ahead and implemented inference on custom FPGA. This is thoroughly unoptimized, so I can't comment on this too much, but you know, there's no DSPs used, there's no DDR bursting. We wrote a custom assembler for a custom instruction set, which was used to convert custom assembly files into an instruction ROM, which included ternary operations. And I don't know, there's a bunch of numbers. I think the things that I really care about are that we were able to achieve 23.8 tokens per second per user, so nothing is pipelined, at 13 watts. And if you compare this to the brain is really working at a human readable throughput of 5 to 15 tokens per second at 20 watts. And so this is pretty valuable information where we're achieving pretty impressive numbers for throughput per user. The next thing to optimize would be aggregate throughput. If you have many accesses, many requests from different users in there. Bunch of numbers that the thing I want to highlight is that when we compare the latency of the core versus memory, the main thing is that it's not memory that's bottlenecking our performance. right? Which is kind of interesting because normally it's always about memory and data movement. But I think that at the moment it's so the three required ternary linear layers are taking up nearly all of the execution time. But in future work, when we introduce parallelism and caching and using DSPs, I feel as though that's going to change the balance a fair bit. So that's, I think a pretty interesting point, but some takeaways. So we've got lessons for SNNs, for spiking neural nets, and lessons for RNNs. Spiking neural networks were already doing what a lot of linear RNNs are now introducing. So element-wise recurrence, right? We did that, but just without the theory to back it. And now we know why it's useful and why it works. But the reality is that SNNs are only going to be competitive for deep learning if they're linear over time. We can train at large scales, which might involve removing reset, and also taking some of the theory on, perhaps oscillations, complex eigenvalues, gating mechanisms. And we need to expand and enhance SNNs to account for that. And not just that, but I mentioned sparsity, right? From SNNs, the only reason they're efficient on neuromorphic hardware is because of dynamical sparsity. So it doesn't really matter if it's a binary activation, as long as there's sparsity, that's what's key. Some lessons for linear RNNs is that we found that forget gates are critical to account for the lack of these huge ass attention matrices, right? We still have a lot to learn from the brain. Like we introduced constrained forget gates with the lower bound as an idea that was inspired by cortical processing at a very high level, right? But it still helped so much. And finally, we learned that static sparsity, which implies that, ternary parameters introduces about 30% sparsity as a result of having a bunch of zero weights. That is far easier to scale and far easier to train than dynamic sparsity. So dynamic sparsity came from SNNs, that came from Spike GPT. That was difficult to scale, but our MatMul-Free model just seems to keep scaling, which is nice. But maybe we're doing something wrong. Maybe we need to introduce dynamic sparsity without binarized weights or without binarized activations. Maybe ternary activations are the way forward there. Now, finally, this is obviously work that isn't possible just on my own. I think the neuromorphic computing group here at UCSC carried the weight of this. In particular, Ridger. So Ridger over here in the back row, he is the first author of Spike GPT of MatMul-Free. He's an absolute star and has been doing some incredible work that's really changing the way that we're doing neural networks. A set of references of different work that we've done and also work that we were inspired by. So some of the work on forget gates was inspired by HGRN, and oscillations of hidden states are also in there. Mamba started doing some work that goes towards element-wise recurrence, and Legendre memory units are kind of the first justification of linear recurrent models, whereas everything up here, SNN Torch and Spike GPT and MatMul-Free, are some other papers that we've done. So with that being said, I am not surprised that I've gone well over time. Sorry about that, but I just got a lot of things to say. So with that being said, anyone that's still alive and listening, I'm happy to take any questions.
Wonderful. Thank you very much, Jason. Don't worry about the time. Like usually we have this buffer, we take from the launch time. Anyway, so let's open up the floor for questions. So we'll basically just unmute yourself and let's get to it. Yeah. Paul, go ahead.
Hi, so this is a fantastic presentation, Jason. Thank you. This has really filled in a lot of holes for me. Connecting it with the Heaviside step function really lit a light up for me as understanding where it comes from. So the question is this. So in your description of the transition matrices, you go from left to right with the output matrix on the left-hand side of the equation, followed by the equal sign, then the transition matrix, followed by the state matrix. You then go on to give a set of values for T2, time 2. So here's the question. Have you explored the counterfactual with inverse or transpose matrices and going right to left in the commutativity instead of left to right?
No, so I personally have not. Although, has the literature done that? Bidirectional LSTMs seem to have gone in that direction. That may resemble what you're describing. Is there any work on bidirectional LSTMs in large-scale language modeling? Nothing that I've come across. What could be possible? Something that I have seen a lot of is combining, I guess, this representation that I've got up on screen here, where you go from left to right, you have some sort of causality with self-attention, which it's not the anti-causal case, but rather just, I don't know, a bunch of inputs, bunch of other inputs, and they just have access to each other. So I feel like it lacks direction. It's just a bunch of inputs that are operating in parallel. We've seen that working in tandem with the causal case, that improves performance significantly. So literally 2 days, what was it, 2 days ago? This paper came out, Jumba 1.5 with another language model. And what they did was combined state space linear recurrent models with attention. And then prior to that, Samba, which found that roughly if 95% of your model or 90% of your model is linear recurrence, 5 or 10% of your model is attention, then you're able to basically get better performance than either of the two cases alone, which I thought was really, really impressive. And I kind of expect that having bidirectionality should resemble that case with Samba. So it could very well be worth exploring. It could be the way to reduce the cost of that 5 to 10% of attention. So definitely worth exploring, I think.
Thank you.
Yeah.
Hisham.
Yeah. Thank you very much, Jason, for your excellent presentation. But I would like you to comment on the work that being done in the applied brain research, which is a startup that started by Professor Chris Smith in Waterloo. I see some not overlap, commonalities between what you do and what he does. So I want you to comment on this.
Yes. So Legendre memory units, Chris Elias Smith. So you were being very respectful by saying that it's not overlap, but there is absolutely overlap. So a lot of the work that I'm presenting really was kind of based upon things that Aaron, Ivana, and Chris did from Waterloo in 2018, 2019. So what they did was introduce LMUs. Now, what that does is that they started with recurrent neural networks. They said, cool, we've got an RNN. Instead of using backpropagation through time to optimize the recurrent weights, which I denoted as beta in my previous slides, they said, let's instead analytically calculate what they should be. We can analytically calculate them by taking the input activations over time, and I don't know, let's use the Legendre polynomials to optimize the recurrent operations. And in doing that, we can remove nonlinearities through time. We can also train everything in parallel because we now are doing things analytically based on the input alone. So my parameter at t=3 doesn't need t=1. So really, that was the onset of using linear recurrent models effectively. And they benchmarked it on pretty small scale tasks. They introduced a spiking neural network that was optimized using this approach with parallelism without backprop through time and all of the good stuff. Following that, Albert Gu, who was at Stanford, I think he's at CMU now, he took a lot of the work from Chris's group and he basically fed it steroids and made it scale up insanely well, leading to work like Mamba that is doing very, very competitive language modeling with a lot of Transformer++ based architectures. That's led on to a whole heap of other work, ours included. So if I had to describe MatMul-Free, I would say that it's something, so Mamba led to a lot of other work such as HGRN, etc. So if I had to describe what our work is, it's basically HGRN2 combined with BitNet, combined with some principles from Mamba, combined with a bit of Spice and some ideas from SNNs, and then bam, MatMul-Free. So really, we're really just standing on the shoulder of much larger giants than ourselves. But everything Chris has done has been damn awesome and very relevant to the work that we're doing.
Wonderful.
Thank you.
Do you want to unmute and ask your questions?
Sure. Hi there. I want to thank you for your work and for your presentation. It was very useful. Great summary. Awesome. Let's see. I had a bunch of questions, but probably the most burning one is your experiments with the FPGA, or what's your heuristic experience? So you've mentioned that it's not optimized. That's understandable because that's hard. But have you seen any savings so far?
Yeah, so I mean, it's hard to say if there's been any savings because we're not really doing any, we haven't yet done any one-to-one comparison. So we haven't built a custom implementation of Transformer++, for example, and done a perfect comparison. That would be useful to do. That would give us a good quantified analysis of like how much benefit do we get from using state space models over conventional transformer models. If I had to give a bit of intuition, I'd say that you'd get savings from two things, but I really can't give an order of magnitude estimate or a factor of improvement estimate. But there'd be two things where we would get benefits from. One is the use of ternary parameters. So something that I'm sure self-attention and Transformer++ can milk the benefits of if targeted correctly, and that's what BitNet showed. But I feel as though linear recurrent models are far more robust to ternarizing parameters. And so that's something that you're able to get some benefits out of on FPGAs that other non-linear recurrent models seem to struggle with. The second benefit is as you move forward through time, as you move forward through sequence steps, you're using far less cache than self-attention. Self-attention, every step requires an increasing state. Actually, Mamba kind of observed that, and they said, all right, well, if self-attention requires an expanding hidden state to get good performance, well, then let's just combine expanding hidden state with linear recurrence. And so that's good because you're kind of ticking the box of what is the challenge behind making recurrent models compete with self-attention. It's bad in the sense that now you're suffering from some of the drawbacks of self-attention, and that is an increasing KB cache. It's bad up to a point because I believe that they have a bounded hidden state that doesn't necessarily scale with the input sequence length, I think. Don't quote me. But they kind of prefix their the hidden state size in Mamba. So you know what you're going to get. In our case, yeah, we have far less reliance on caching, far less reliance on, I suppose, if you're going to store those values in SRAM, there's far less SRAM that we need on chip, or perhaps you can use that SRAM instead for weights. So it's, yeah, really difficult to give you a cold, hard answer. But those are my intuitions on where we would win in terms of hardware benefits if we did a perfect apples to apples comparison. Really, we need more FPGA designers in my group. That would be nice.
Follow-up to that is you mentioned the things about the backpropagation and also memory boundness. So you mentioned that you don't suffer from memory boundness, which I found interesting because generally this is the problem with linear recurrences. Being too not dense enough of an operation in terms of flops.
Yeah.
And
I don't want to say that we suffer, that we don't suffer from memory boundness. It's just that it's scale. You reach that memory bound far slower than you would with backprop through time. Yeah.
And you said backprop through time that linear scaling is too heavy, which I found interesting because this is trying to compete with transformers being two orders of magnitude higher in terms of the computational complexity. So, sorry, I have not read the background on SNS. Could you specify how you're doing better than linear?
Sorry, was the question how are SNNs doing better than linear recurrent models?
Yes.
Oh, yeah, they're not. No. They're so they're absolutely not doing better than linear recurrent models. So let me add a few caveats. If SNNs remove the reset mechanism, then they are a linear recurrent model.
Mm-hmm.
SNNs add that constraint of binarized activations, which also degrades performance significantly. And so one of those kind of final lessons that I would say is that, no, I didn't list it here, but the point that I want to make is that binarized activations doesn't matter. But if you have hardware that can handle dynamical sparsity that is better with, I suppose, workloads that are not procedural, then SNNs might make sense. So for a given amount of inference compute, then you might be able to outperform the equivalent case for a linear recurrent model. But without that, I don't think it makes sense.
I see. So it's the nonlinearity on the reset.
Yeah. The purpose of this presentation is not to sell everyone on the dream of spiking neural networks at all. They are so difficult to train. Anyone that has used SNN Torch knows the pain points of SNNs. But really, the point is that they had a lot of lessons. I kind of think that, you know, Chris's group was doing a lot of work on spiking neural nets, which then led to them working on LMUs by adapting some control theory into those models. And so, I mean, as a result of that, there were a lot of lessons that we learned from SNNs as to why linear RNNs work effectively. A completely different deep learning community derived separately to us, which is kind of cool. Like it's really cool to come to the same result. They were doing it far more theoretically, we were doing it far more applied, and then they totally overtook us in terms of what applications were out there. That's kind of beautiful. It felt like, yeah, we were on the right track. These guys just, yeah, looked at how language models were doing it, and they did it a hell of a lot better. But that let us do it, let us kind of catch up and keep going using everything we've learned previously.
Awesome. Thank you for that.
All good, Philip.
Wonderful. Anyone else? Questions?
There's only one thing I was going to describe here, and that is that this idea of forgetting gates seems to be really similar to the notion of discarding, which is in quantum theory.
Oh, yeah. That is fascinating. Yeah, yeah.
I put the link to this paper in the chat, but basically this is time symmetry in quantum theories and beyond. And our friends Bob Kirker and Stefano Gurgusio and John Selby are the proponents of this idea. So time symmetry in quantum theories and beyond. It's by John Selby plus.
Wonderful.
All right, so I just wanted to connect the dots here between two important subjects in my life.
Yes.
This is awesome. All right, I got to add this to my, I think we all have to add this to our to-read list. This is cool.
Yes.
No, I mean, the whole linear recurrent space, that exploded because of the link between control systems and control theory. Maybe this is the next thing to jack up how well forget gates perform. Maybe we're not looking closely enough to quantum theory.
Yeah.
Maybe we can tap into some of the quantum funding.
Yes, yeah. There is way too much of that, so let's do it.
Yes. Okay,
That's-
Bijan, you want to ask a question?
No, I don't want to bog down everyone. I really enjoyed this. I'm struggling, to kind of contextualize where this is headed versus some other improvements. And I'm just, it's amazing the amount of improvement that you've shown here. I've also looked at some other methods, like today, I think there was something I put on LinkedIn about network improvements and things like this. So there's just so much happening here. It's hard to get my mind around all of it.
I know. Likewise, like putting together this kind of presentation has been mind-breaking because you're trying to synthesize 12 months of literature that changes every 2 days, and it hurts. But having said that, the my observations are something like this: that there was a really neat plot that was stupidly simple, but it makes a lot of sense, and it showed how much of time your GPUs are spending in each process of self-attention. The self-attention, yep, sure, that had some cost, but the dominant was really the linear layers, the feed-forward layers. It wasn't the attention matrix. The attention matrix was the second largest, and so, doing MatMul-Free, removing self-attention helps your second largest operation. What about your largest operation? Okay, so linear layers, we managed to replace the weight matrices with ternary parameters, so that still helps. But maybe the paper title, MatMul-Free, it might give people the wrong impression that that's the goal. That's all we're trying to do. No, like, matrix multiplication, sure, large computational complexity, but if it gives you so much better performance in terms of memory, in terms of context, software level memory, then maybe you should have a little bit of it. And optimizing your linear layers is the main thing that you want to target. And what we've really learned here is that ternary parameters are totally fine. As long as you do your gradient approximations, etc., that's able to crush the main driver of latency in self-attention. So I really like where the hybrid language model space is going, which combines linear recurrence with conventional self-attention. That feels like that feels like a one dominant path, a pathway that we're not seeing so much of. And I think this is just a function of the hardware lottery. We're not seeing much in dynamical sparsity. So, I mean, sparse weights, NVIDIA GPUs are pretty well optimized for block sparse matrices and handling those. But it's only a very niche set of hardware that can handle sparse activations and things that are not very commercially available. Like Intel's Loihi is one example of what's out there. But I feel as though if you put a bunch of chip designers into a room with a bunch of deep learning engineers, then dynamical sparsity makes a lot of sense to me, because especially for processes where you have many people making requests, like a multi-tenant model where you have many users requesting things that don't depend on each other, but that can fill up a pipeline. Or alternatively, if you have temporal sparsity, so a model that is distributed over time, which is sparse over time, then perhaps the architects could find a way to do memory accesses that don't collide, that don't conflict with one another over time. But really that requires more sparse models. So that dynamical sparsity seems to be an exploratory thing that goes forgotten about because the hardware is not there to support it. But if it was there, then I feel like we would potentially dominate what is out there at the moment. For things that are immediately useful, immediately practical, and yeah, the hybrid model space seems to be a very promising one.
Yeah, it's funny that you mentioned that, because I just finished something. We had a discussion about cans, and so the application of cans is really desirable in one kind of use case. And but this really kind of your approach here is a game changer, because for time series data, the RNNs are awesome, and so by using the extension that you're outlining here, I could see having to kind of overhaul the whole model methodology for a while and kind of optimize what we have.
Yeah, no, I agree.
All right. Any more questions? Victor, go ahead.
Yes, hello everyone. Thank you, Jason, for the talk. It was amazing. I wanted to know if you see or if you foresee any advantages of using other neuron models other than the exponentially weighted integrating fire, the leak integrating fire model.
Yeah, I think the second half of the presentation kind of got at that point where if I was to fly back to the high-level architectural overview of the MatMul-Free model. So, I mean, you could consider this whole sequence of operations to be its own sort of neuron model, where, look, you've got some forget gate mechanism. So if you looked at a leaky integrate and fire neuron, then you would just replace this with beta. You would just replace these three values with a scalar that is not learnable. That scalar is multiplied by your hidden state, and you add an input. MatMul-Free just changes that a little bit by replacing beta with the forget gate. So that forget gate has that lower bound clipping that introduces that idea of deep blocks having longer memory, early blocks having shorter memory. You sigmoid that because you want everything to be between 0 and 1. You either want to forget something if it's closer to 0, you want to remember something closer to 1. You don't want anything outside of those bounds. So we sigmoid the forget gate. That's scaled by the hidden state. So you already have a data dependence in F1. That data dependence F1 comes from a set of other operations. So that weight matrix is initialized. Yeah, maybe don't worry about that, but there is data dependence in how F1 is calculated that isn't shown here. This 1 minus sigmoid is just a discrete time solution to a low pass filter, which is basically a leaky integrator. Except instead of multiplying it by the input current injection, it's just multiplied by C1, which could be thought of as the control gate. Really, it's just the output of another dense layer. So it bears a lot of similarities to a vanilla leaky integrate and fire neuron from SNNs, just with some subtle changes here and there that were developed largely by the linear recurrent model that doesn't really talk to the spiking neural network community other than Chris Elias Smith's people. But that's changing now. That's changing. We kind of realize that these two things are very similar, just with a bit extra, but with a bit of extra spice. So as it presently stands, this is probably the best token mixer that exists at the moment for linear recurrent models. That will, I have no doubt that will change within a few weeks. if you want to see that in action outside of ternary parameters, HGRN2 goes in that direction, and they're doing pretty well. There are a set of limits. So I do want to be very transparent about the limits of linear recurrent models. And so the benchmarks that I showed you, all well and good. There is one kind of pathological benchmark called needle in a haystack. That's where linear recurrent models seem to break down a little bit. The needle in the haystack benchmark's really fascinating. So take a sentence, San Francisco is a beautiful city, put it at the start of a PDF. PDF could have 1,000 tokens, 2,000 tokens, 8,000 tokens, and so on. And at the end, I say, what is San Francisco to my model? And hopefully it tells me that it's a beautiful city. That sentence is the needle. The rest of the junk in my PDF is the haystack. And you can basically move where that sentence is through your PDF. And it turns out that from self-attention-based models, if I have it as a first token, it does really well regardless. It puts a lot of weight and emphasis on the first thing in your model. If I put it one sentence later, or a set of 1% depth into my PDF, performance degrades, and then it starts to improve again as it gets deeper and deeper and closer to when I ask my question at the end of the processing. So that's the needle in a haystack benchmark. Self-attention does a pretty good job of it. Linear recurrent models are pretty shitty at it. And so I feel as though linear recurrent models seem to be quite bad at memorization. They're bad at copying. Maybe they're good at understanding. I don't think any benchmark exists out there that pits memorization against understanding. So they're good at the benchmarks that seem to be the de facto standards of what we look at. But yeah, memorization kind of sucks. So I'm sure that something is coming that does hopefully change that. Or maybe it's a matter of going towards hybrid models to fix this. But yeah, it was a very simple question what you asked, but with a very loaded answer because there's so many things to it, right? But yeah, a lot. One sentence answer. Yes, plenty of different neuron models that can be expanded upon LIF neurons to help.
It makes a lot of sense. I hadn't thought of the slide as the neuron model in your neuron model.
Yeah. Anything's a neuron model.
Wonderful. Philip, you want to ask a question?
Oh, I was just gonna note that breaking the linear time invariance has helped with these types of discrepancies in the needle in a haystack benchmark, but it's still not up there with attention.
Yeah. I didn't know that, but I appreciate that. It makes sense. Yeah.
That's the contribution of the Mamba paper, or also known as S6. One of the S's is for selectivity, which is breaking the linear time invariance that was used previously when you were talking about the long 1D convolutions. So they calculate the kernel, which is the expensive part, and then they use it to calculate the 1D convolution. Mamba can't use that because of the linear time invariance being broken.
Gotcha. Okay, that's interesting to know.
I think all the Mamba folks use LoRa a lot, so.
Yeah, LoRa seems to really make a play whenever, actually, like Apple uses LoRa to introduce 4 different heads for 4 different tasks when they don't want to retrain a bunch of different models within I guess the space that an iPhone has to offer. I think they have like a 2.7 billion model on there. But then if they want to do something for auto predict on steroids, text correction, or whatever of the 4 different tasks, and they use a different head from that is trained via LoRa. That seems to be like the most fancy application of it. Would it be useful in enhancing memory? I have no idea, but could be cool to look into.
Perhaps I still do have a question, which is if you could highlight, if you do have the comparison in your head, if you don't, it's fine, the differences between the SNS movement and the linear RNNs and SMs, particularly the diagonal case, which is the structured.
So yeah, on the diagonal side of things, that's all identical. Other than SNNs, I don't think anyone has yet. Maybe they have in the past couple months, and I've just missed the literature. But they don't use complex eigenvalues in SNNs. There's no reason why you can't. Then it just that looks very much like a state space model. But yeah, really the only fundamental difference that I think that is out there is a spiking neural network is basically a linear recurrent network with binarized activations and a reset mechanism. Many people don't use the reset mechanism. Intel's low-EHE hardware and Synsense's cute little Xylo chip for SNN workloads have kind of relaxed that, and they use graded spikes, which just says, cool, you have a spike, but now let's weight it by another factor. So it just may as well just use a shifted ReLU or something to elicit that. And it just goes back to being non-binarized. So really, SNNs are synonymous with sparsity. Like people think of sparse activations when you bring up SNNs. Linear recurrent networks don't have that constraint and are a little bit more flexible, a little bit more free. If I was to write an SNN paper and I decided to start introducing all of these extra operations, the reviewer might say, "Is this really a spiking neuron? Because you haven't derived it from biology, you've derived it from it working." So, like in that case, yeah, it's just really a feeling. Like I think it's there's no real clear distinction because there's too many similarities. But
I see. So there's a lot of similarities, but SNS tends to be more biologically inspired, even though our neuroscience friends will forgive us for the comparison.
Something like that. I do find that the neuromorphic brain-inspired people come up with a lot of ideas to a small scale. They do it, and then another community might adopt it. So in this case, Chris's group came up with SSMs, with state space models, and then the rest of the world kind of picked that up and really improved them. And then they stop being branded SNNs. They stop being branded neuromorphic. It's really just a branding thing, to be honest. I don't really give a shit about the branding. I mean, at the end of the day, if it works well, it works well. And so yeah, the distinction between SNNs and state space models is very superficial, I think. Maybe someone would disagree with me, but it doesn't matter. If it works, it works.
So one thing about the reset capability, like can for example a multiplicative decrease be used instead of reset?
So in a way, if I pull back that equation for spiking neural models, how far back do I have to scroll? So this was my SNN. Let's just look at this first equation. So having a reset is like saying subtract S there. Forget about subtract S, but here we already have this multiplicative decrease from W being between 0 and 1. So you could say, all right, I want a multiplicative decrease only if we have a threshold crossing.
Yes.
That still requires a threshold crossing, which is a nonlinearity, and that breaks the ability to train this in parallel. So the moment in that computation, if I bring up the computational graph, this messy dude. So the moment I have something from a spike feeding back down to the time series pathway, then I break parallelism. So if I'm gating a multiplicative factor using S is a function of a nonlinearity. Therefore, I can no longer do this properly. And I have thought about this exact comment that you just made as well. It could be that you don't do a hard threshold, rather you just, I don't know, if your membrane potential gets larger, then your decay rate increases faster to represent that you're about to spike. That's acceptable. That could be cast into a form that isn't nonlinear.
Yeah.
Maybe that could be worth checking out. That could work.
And a crosstalk, like let's say a what do you call it? Like a purposeful crosstalk might also open, but I don't know, like the moment you add these things and you break through like these linear fashions or something, your training will be out of the window. Looks to me like we are trying to do we're trying to do like this biomorphism. I mean, we have always a tendency to do this, but biomorphism might not be necessarily the best thing. It's the best thing for biology to go through. I mean, there are tons of examples, like the flawed design of the knee, and like, I don't know, it goes on and on. Like the fastest, I don't know, like we have Formula One, I don't know, cars, they don't use legs. They beat the cheetah, like, you know, by a scale. It's like,
Exactly.
I mean, somewhere else wheels, like let's say, showed up in a rotifer or something, like much different. So training on its own is like, I mean, we have this whole backpropagation, which is basically just Newton-Raphson method, like on scale, and that's it. We don't have anything better. And then now we're bounded to what we can do that adopts like the backpropagation, because otherwise, how do you want to train it? But it's like, maybe we should look at training. Maybe like, I don't know what Paul brought up, like maybe some of these quantum-based methods, like where we use like, let's say entanglement and like, things like, I mean, at that scale that the brain is, the quantum effects are all over the place. Maybe these things should somehow come in, but then we are computationally simulating what is the brain, like what are these things doing, and then we expect them to behave the same way. Of course they're not. And that's why your approach to like go through like leaky capacitor and all of these things, it just, I mean, this whole approach of like SSNs, like, which it's been around, I think, like less than 10 years. I think it's a good way to go through, but then it should break through this glass ceiling. Like, just simply like, computational, we probably will not get much. You get just whatever you get from a von Neumann machine. That's it.
No, I completely agree. That's kind of like the ethos of my research group. Don't copy the brain for the sake of it. Copy it because it makes sense. And if it doesn't make sense, don't do it. I mean, evolution had access strictly to sodium ions, chloride ions, potassium, calcium. Silicon is not any of those things.
Yes.
So it doesn't make sense to copy neural processes into silicon. Probably not. I mean, the brain has sparsity. Okay, copy that. Do all neurons have this feature of sparsity? Do all brains use spikes? No. In what is it? There are small little organisms that don't require long-range communication, and in those cases, the membrane potential of those neurons do not work with spikes. They use graded action potentials that gradually increase, nice and smooth. What is that to say? Are spikes necessary? No, spikes were just evolution's answer to communicating between your brain and your toes very quickly, right? That seemed to be the problem they were addressing. So, data movement is an issue. Sparsity is a good direction for data movement. But the moment you start copying the exact shape of the action potential, introducing the reset mechanism just because you feel like it stops making sense, right? So, yeah. Engineering first, brain second.
Yeah, I watched, I will try to remember the name of the philosopher, like he was talking about very similar, like, let's say, where is this silicon-based approach is taking us in terms of AI, and like, how far should we look into it? Should we just look at like classical functions that you get like from transistors and switches and so on, or you can go deeper? Because I mean, I mean, his analogy was great. Like, he was saying like, yeah, just consider like, let's say, tubes and pipe water and everything and so on. Like, that's a switch. So can this become like, let's say conscious or something? I mean, he took it all. It's a philosopher, right? So any more questions? I think the length of this presentation broke the record from, I think, I'm not mistaking, Helmut from Swabian, like, was last time it hit this an hour 45. So congrats, I think you passed that. And if we don't have any more questions, we'll adjourn at this point. And then just like want to tell everyone about, like, in 2 weeks, we have a presentation by Emily Caldwell about physics, free space. It's like a physics related thing. So it's about free space, optical time transfer principles and applications. And know any more comments or anything, we'll see you guys in 2 weeks. Thank you again, Jason.
Awesome. Feel free to email me because there was some really cool conversations. Paul, Philip, like, yeah, it would be awesome to stay in touch. So yeah, I just sent my email in the chat.
Absolutely. All right. Bye, everyone.
See ya.
Bye. Thank you.